Okay, so I'm going to start off with the warm-up. R equals for cosine 3 theta. I'm going to use our shortcuts here. So it's 3 theta, so I know it will have 3 petals. Each one is going to be 120 degrees apart. The max radius will be 4, because of that right there. This is cosine, so it will start at 3 theta equals 0. So theta equals 0 is where it begins. So 1, 2, 3, 4, and then I'm just going to go 120 away. Boom, and boom. Here we go. Now it is important for you to be able to connect this back to the original graph, okay, like this one way over here, and what quadrants this actually falls into, right? That this part is the part in quadrant 1, this part is actually the part down here in quadrant 3, this is quadrant 2, and this is the little section in quadrant 4. We're going to use that a lot towards the end with the advanced graphing techniques. Ooh, r equals -2 plus 3 sine theta. So this is one of the limacus, the limacons, as it were. I'm just going to do a quick sketch of its graph because I find that useful for me. So I'm going to be down here at -2. I'm going to go up to 1 and down to -5. Tricky, tricky. Sine goes like this. And I'm going to stop right there and actually plot some points here. So when I'm at 0, I have a negative radius of 2, so that's going to be here. Okay, when I'm at pi over 2, I'm a positive radius of 1. At pi, it's a negative radius, so that's going to be over here. At 3 pi over 2, it's -5. So 1, 2, 3, 4, 5 will actually graph up there, and then we end right there. So I just wanted to get that out of the way so we could get some of these points here. Next, we're just going to use our little shortcuts, which is that we just do the 30s for sines or the 60s for cosines. So when I do this, I get -2 plus 1.5. That's going to be a -1/2. So for 30, it's a -1/2. That's going to be right there. And for 150, it's a -1/2. So that will be right there. We'll do this again, but this time subtracting. This will be for the negative quadrants. So that's going to be -2 minus 1.5. I'm pretty sure that's -3.5. So when I'm at this angle right here, it's -3.5. So it's actually going to graph up here, 1, 2, 3.5. And then when I'm over here, it's also negative. So that's going to graph up here. Okay, I recognize that this value is smaller. I'm basically, this is flipped because it's negative, but I have this inner section here that's going to give me the inner loop. And there you have it. Last but not least, for the warm-up, we have r squared equals 9 sine 2 theta. I'm going to cheat and treat this one like a 2-petal rose curve, which means that it's 180 apart. Its max r, this is where it's a little different, is going to be the square root of 9, so that's going to be 3. Its sine, so when it starts, I'm going to set 2 theta equal to pi over 2. So theta is going to equal pi over 4 as my starting point. Out at 3, 1, 2, 3, 180 away. It's going to be there. 2 petals, boom, boom, donezo. So let's start off by just graphing both of these. We have r equals 3. That's just going to be a perfect circle centered at 0, 0 with a radius of 3. And this guy right here is going to be one of the limacus. It's going to be a heart-shaped thing going up. And I'll just overlay that graph over here. And if we look at that, you can kind of see where there might be intersections here, but it's a little bit trickier than that. Just because the graph intersects doesn't mean that they actually line up at the same angle, okay? So it's similar to the way that parametrics were, where we needed to not only intersect, but intersect at the same moment in time. Here we need to make sure that we intersect at the same angle as well. So what we're going to do is just set these two r values equal to each other. So we'll get 3 equals 2 plus 2 sine theta. And then I will just solve for theta. So I'm going to subtract this 2 over and divide by 2. I'll get 1/2 equals sine theta. Okay, so let's see. That's positive, so it's in both of those quadrants. So I'm going to get theta equals pi over 6 and 5 pi over 6. And I'm not done yet because the intersection, just like normal, is always a point. So I need to figure out what the radiuses are that go with this. And we're pretty lucky this time around because we know the radius has to be 3 because one of our equations is just r equals 3. So my two answers are going to be 3 pi over 6 and 3 5 pi over 6. So this intersects twice, which is what we thought. And there we go. For B, again, we'll just sketch a quick graph of it. This is going to be a 4-petal rose curve that starts at pi over 4, and this is going to be a circle that opens in the y direction. And we can see that it's a lot harder for us to figure out where the intersection points are, but they look like there's a lot of them. So rather than relying on the graph, we'll rely on algebra. So let's take a look at these two equations. We'll just set the two r values equal to each other. So I end up with that. And way back in the day, we learned how to solve equations. One of the main things we didn't like was when these weren't the same. So I'm going to look at our favorite formula sheet and remember that sine of 2 theta is actually going to be 2 sine cosine. And I'm just going to eliminate the 4's right off the bat so I don't have to think about them. So I'll get 2 sine theta cosine theta using the identity equals sine theta. And I'll just subtract this to the other side. And I can factor out a sine theta now. So I'll get sine theta times 2 cosine theta minus 1 equals 0. That gives me sine theta equals 0 and cosine theta equals 1/2. So sine theta equals 0 at 0 and pi. So I'm going to get theta equals 0 and pi. Cosine theta is going to equal 1/2 at, let's see, what is that? Pi over 3 and 5 pi over 3. Now I just need to take these and figure out what the what the radiuses are. So I always find it easier to plug it into whatever the smallest equation is. So it's going to be this one right here. So if I plug in sine of 0, I'm going to get 0. So that's going to have a radius of 0. So this one gives me radius 0, angle 0. Sine of pi, that's going to also give me 0. Times 4 is still 0. So this one gives me 0 comma pi. So radius of 0, but an angle of pi. And that's pretty neat because we have two different intersections at what is essentially the same point, but they happen at different moments in angle time, if we think of angles as time. We can do pi over 3. That's going to be sine pi over 3 is going to be a square root of 3 over 2. So times 4, that's going to be a 2 rad 3 pi over 3. 5 pi over 3, that's going to be a negative. Same idea, so I'll get a negative 2 rad 3 5 pi over 3. So these are the 4 different intersection points. Even though these guys end up at the same exact point in the center, they happen at different angles, so we have to count them as separate. So when you sketch a graph of this one, we have two 4-petal rose curves, and it's just way too complex for us to visualize and see where any intersections are. So we definitely can't rely on the graph for any guidance. So we'll begin by just setting the equations equal to each other. So we'll have sine of 2 theta equals cosine of 2 theta. I will divide cosine to the other side, so I'll get tangent of 2 theta equals 1. And I'm going to solve for 2 theta. So remember, that means I'm going to go around the circle twice. So when I do this, I'm going to get pi over 4 and 5 pi over 4. And then I just need to add 2 pi to both of those. So I'll get 9 pi over 4 and then 13 pi over 4. And that's because of the 2 theta. And then I need to divide everything by 2. So I get pi over 8, 5 pi over 8, 9 pi over 8, and 13 pi over 8. And all of these are back down between the 0 to 2 pi. So that's why we end up doing that. Now I need to figure out what the radiuses are, and that's just super fun, but it doesn't matter which one we plug them into. I'll plug it into sine. And what's nice about this is that it's 2 theta, so I can actually just plug these angles in. I don't need to think about the fact that I'm plugging in the pi over 8s. I can just say, okay, when I'm at pi over 8, I'm really going to do sine of pi over 4, and that's a square root of 2 over 2. So I'm going to have square root of 2 over 2, comma, pi over 8. When I do 5 pi over 4, I'm really evaluating sine at, 5 pi over 8, I'm really evaluating it at 5 pi over 4. That's going to be negative. So I get a negative square root of 2 over 2, 5 pi over 8. For 9 pi over 8, that's the same thing as doing 9 pi over 4, which is the same as doing pi over 4. So I'm back to positive square root of 2, 9 pi over 8. And the 13 pi over 8 is the same thing as 13 pi over 4, which is the same thing as 5 pi over 4, which means it's going to be a negative square root of 2 over 2. You see, I'm not reinventing the wheel here. I'm kind of using some of my previous knowledge over here to help me figure out what all 4 of these intersection points are. And there was no chance I ever would have seen those in the graphs.